Uh, Austrian Institute of Technology in Germany, we develop and implement a digital measurement system based on Raspberry Pi. In short, DMSRP, to foster STEM education. The objectives of this presentation are to emphasize the contribution of the MSRP as a technological tool and rich learning environment in STEM. And then I investigate on both hardware and software capabilities of the MSRP to enable integration of STEM, proactive learning, to authentic learning, so as to meet the requirements of key characteristics of integrated STEM, which are the centrality of engineering designing, developing of STEM practices, content and context integration, and supporting of 21st century skills, including collaboration, communication, creativity, and critical thinking. We shall be going through the following content aspects. First, I want to explain what exactly is the MSRP and its benefits for STEM. Then a few words about the potential of the MSRP. Then how the MSRP-based environments interconnect science, engineering, and technology. Then we go through the case study of Fraunhofer diffraction, where the students use the MSRP to design and to realize a low-cost diffraction scanner with which they learn physics of waves and at the end some conclusions. So the DMSRP is a low-cost accurate measurement system for science and engineering projects, which allows acquisition, display, and storage of data from a wide range of sensors. The Raspberry Pi is a single-board computer system having all the features of a personal computer, including the dedicated processor, having graphics and memory, and it has also a micro SD card where the students can store their measurements and data. Like for instance, we use normally a 32 gigabyte micro SD card. The Raspberry Pi has internet connectivity, so the students can transfer their measurements and files over the internet. A very powerful computation capability. So Raspberry Pi can run emails or LibreOffice application, and of course the 40 GPIO pins. So a lot of low-cost but accurate sensor can be connected to GPIO pins to carry out measurements. Within the DMSRP, we have integrated a lot of sensors in the last 6 years. So on the right-hand side, we see the digital sensors for measuring different kind of physical quantity, covering almost all chapters in syllabus. The digital sensor, they have most of them an I2C compatible interface, allowing a direct transmission of measurements to the Raspberry Pi. And for analog sensors, like for instance, here we have mini load, a cell for measuring forces, or thermistors for measuring temperature, or linear Hall sensor to measure the strength of magnetic field. Those have to be interfaced with the Raspberry Pi via an analog digital converter, which we choose after searching RDS1115 with 4 channels and with embedded amplification. So for the case where the signal to measure was too low, in that case, we can integrate into the system operational amplifiers to boost the voltage to the necessary range so the conversion can begin. What we noticed during our experiments and projects is that measuring with a sensor within the MSRP, brings comparable results, or in some cases even better than those the students get with the commercial systems like PASCO or CASI. Why is that? Because the sensor choose with work with Raspberry Pi can be optimized in terms of precision, resolution, and measuring range. The software was developed by Professor Fast, and it consists of a package with classes programmed in Python for data acquisition, display, and storage of measurements. The whole architecture and classes, information about that one can find under this website. So in order to install the software, first the students have to install the Raspberry Pi operating system on the micro SD card from the internet. Then they have to configure the Raspberry Pi, and at the end they have to install the software with few clicks. So it's easy. And then the students get the interface for all the sensors which have been integrated so far, where they start the configuration first of the sensor to measure with in a file of type YAML. So there the students have to statistics of the sensors in terms of types and number of channels and measuring range. And after they finish to introduce the sensor characteristics, they come back and choose the built-in commands to configure the system, the measurement system, for the purpose of the experiment. So that they have to edit and choose commands for data visualization, for storage of measurements. They have the possibility to introduce the physical quantities and their units. And then after that, they just run the program. So the students don't have to program anything. They just have to choose built-in commands and to edit them for the purpose of the experiment. Then they start to run the program, as I said, and then they get a display window where the measurements are displayed in real time. So the students get immediate feedback of their prior actions, and they can start to analyze the results. In the background here, we have in the terminal all the commands which have been selected and edited by students. Like for instance, here the students enter distance or elongation of spring in millimeter, and they have here in this visualization a history for the measurement. So the elongation is displayed in real time. In the display window, they have buttons for start and stop, for resuming the measurements, save graph. So they have a static representation of the physical quantity which is measured. They can have a button here to save data. And at the end, when they finish the measurement, they close the display window. The benefits for STEM, they are very interesting and important because the students interact directly with a lot of sensors and electronic devices. They work with different kinds of representations and include a lot of structures from all the STEM disciplines, including mathematics, engineering, technology, and science. Also, there are a lot of STEM practices which are involved. For instance, to ask questions and design experiments, work with models, develop and use models, carrying out experiments, modeling with the data, with mathematical tools, using computational thinking. In respect to mathematics, the students work with equation or the inequalities. They build function to model the relationship between different quantities they measure, or they integrate numerical methods for differentiation or integration. Also, the DMSRP promotes content and context integration of different disciplinary areas, and here it's very important to say that these representations are, most of them, student-generated representations, and they are generated for different purposes they set by themselves. Also, there are static representations or dynamic representations. The student can change different kind of measurements while they work on elements of the experimental setting. Also, this kind of representation can be interconnected in order to deep the level of understanding. A lot of modeling approaches are also involved. Here I have an example of multiple representation with DMSRP. For instance, to obtain the current voltage characteristic of a LED recorded with a current and voltage sensor, the students start to choose the suitable electric and electronic components. Here is the case of the current and voltage sensor. Then they think how to connect these components. For that purpose, they can use some specific application and software like FreeSync here to do the schematics. And then they do the wiring on the breadboard. After everything is checked and everything works fine, they can start the configuration of the experiment with the software, where they have here in this case 3 types of visualization. First, the current and the voltage against time, then instant bar charts, so they can compare the measurements of current and voltage, or they can stop the representation at a threshold value of the voltage. Then they have an XI representation, so they have the current voltage characteristics, which they further can model with a mathematical function, which is in this case exponential function, and then they check with the literature for the Schottky function for the diode. Here are some modeling practices with the DMSRP. A lot of mathematics can be here interconnected with the experiment referring to charging and discharging of electrolytic capacitor of a resistor, which is connected at the pins of the Raspberry Pi. So this is the so-called history. The voltage across the capacitor in brown and a step voltage created at the pins of the Raspberry Pi as a wave voltage. So the growth and the decay process can be modeled with exponential functions. Also, the data are recorded and stored in CSV file, which is possible to be processed with a LibreOffice, which is running directly on the Raspberry Pi. Here, the students introduce the natural logarithm to process the voltage across the capacitor. They get a straight lane with a slope depending on the time constant. And then they can modify the values of the capacitance and the resistance to see how the exponential growth and or decay is getting steeper or shallower, and also the slope of the straight lane. Then the DMSRP is I consider it as an integrator of STEM subjects. in terms of cross-cutting concepts, in terms of core ideas, and in terms of including science and engineering practices. Obviously, the students look for patterns in their observation and in their mathematical representations. Also patterns in doing the wiring on the breadboard. When they build different kind of circuitry, they look for cause and effect. If something is not working, they look for the cause for that problem. In terms of system and system models, of course, this is directly connected with the practice of producing or developing models and so on. So in all this process, there is a back and forth process where the students go from the problem to be solved, to the theory, to the engineering design, and to the resources. And here there are some steps of the whole process where they plan the experiment first, choose the appropriate sensors, reach the data sheets of those sensors, look for the physical principles of the sensors. Then they think about connection and communication with the Raspberry Pi, about the digitalization of the signals, fundamentals of electronics. Then they go further, they work on wiring on the breadboard, they configure the software, carry out experiments. They are always involved in trials and errors, and they optimize their circuit, and then at the end, they process their measurements with mathematical tools. And so here are some steps in a chain of structure and iterative engineering design process. I shall not stay too much on this slide because I want to show the interesting things here. So for instance, here, the students use the DMS-RP to design their low-cost diffraction scanner to measure the intensity of diffraction pattern, which was generated like a project-based learning strategy with an open and authentic problem. At the end, after they look for different kind of light sensors, they stop at a photodiode with a price of 70 cents, which is a high-speed photodetector with a high radiance sensitivity. And all the steps have been introduced in a Jupyter lab. Is working, where they describe the steps, so to say. Then they introduce, they have here a video they casted for all the steps. And at the end, I don't have the picture to show how. Moment. I'm in. Thank you. Okay. Thank you. So, and then at the end again, all the steps from the schematics, wiring on the board, introducing into the experimental setting. And here is what the students do. Here is the diffraction pattern with maxima and minima of different kind of intensities. And here I have so behind this hand-cut pattern, the photodiode with which we do the measurements. Here's the whole settings. So we have here a student employed a self-created diffraction scanner into the experimental setting. This is their self-created scanner. Then here is the available setting in the lab. And here is how they record the intensity of the diffractions. What I want to show here is give some levels. It's everything again here in Jupyter Lab, where the learning objectives are put down. Then the generated Python code for the functions they deduced based on the phasor model. Here we have the mathematical function. We have the video. This is very short. I want to show you the video.
I'm sorry, we're out of time.
Okay, thank you very much. So this is it.
Thank you, Marinela.
Thank you.
Any questions?